Well, first of all, of course, let me thank to the organizers for a wonderful workshop and a wonderful program. I'm really happy to be part of it. And since the last talk, you're probably tired, and we have heard a lot about different exotic criticalities in various contexts. And I guess you won't be surprised that what I'm going to do in my talk is to add to this list yet another exotic criticality in yet another context. But what I'm going to try to convince you this 30 minutes is that thinking in terms of simulating quantum phase transition in quantum simulators, we should really push our understanding to the point where we could not only just realize new quantum critical theories, but also to the point where we could tune or we could manipulate quantum phase transitions in experiments, and in particular, for instance, where we could zoom onto something that we find interesting. But let me start from far. Let me start from quantum 1D systems. So in this workshop, there were many talks about quantum 2D or 3 plus 0D, and probably there is a good reason for this, right? Probably this is because 1 plus 1D or 2 plus 0D now seems like a comfort zone for us. And there is a good reason for this, right? We do have very well studied, very well explored conformal field theory in 2 plus 0D, and we do have the notion of universality classes that basically tells us we should not care at all about microscopic details of the system. We look at the symmetry of the ordered phase and we know what's going on. And of course, a textbook example for these universality classes could be an Ising transition, right? Either classical statistical model or quantum 1D chains, or realization in real materials, or even the critical. How to press it? Do you know how to press it? Oh, the real, the critical point of water that terminates the first order transition with twofold degenerate ground state. In all these cases, we know when we go from twofold degenerate ground state to a non-degenerate one, we undergo Ising transition. As simple as that. But if we make our system a bit more complicated, whether such a simple symmetry picture is enough. And my personal interest in this model comes from experiments in Misha Lukin's group on the arrays of Rydberg atoms. So what they do in experiments, they trap ultra-cold atom with optical tweezers with a well-controlled distance between the atoms, and then they shine a laser with Rabi frequency omega that brings an atom from a ground state to an excited state. And when there are two atoms in excited state, they start to interact. And they interact with van der Waals potential that scales with a distance as 1 over R6. So this is pretty steep scaling that almost forbids to have simultaneous two excited atoms within a certain range, or within a certain distance, and it leads to so-called Rydberg blockade. Now, the competition between this Rydberg blockade and the lazy detunion that wants as many atoms as possible to be in the Rydberg state leads to this wonderfully complicated phase diagram with lobes of integer periodicities. And if I now ask you what would be the nature of the transition out of period 2 phase, you would tell me Ising, and you would be right. But the life becomes more complicated and more intriguing once we climb up over this phase diagram and look at the nature of the transition out of period 3 and period 4 phases. And that's what I'm going to focus today. But in fact, these problems, the transition out of period 3 phase, root back to a very old problem that has been studied by Hughes and Fisher, and actually the whole community, in early 80s in the context of absorbed monolayers. So the setup was the following. There is a substrate and then a layer of adatoms, the typical example could be silicium or germanium, that form a crystalline structure. And the question is, how such a crystalline structure, let's say period 3 phase is shown here, would melt as a function of temperature. Naive expectation, we have 3 different ground state domains, 3-fold degenerate ground state. We should expect 3-state Potts universality class, like Ising, but for Z3 symmetry. It turns out that life is not that simple, and what Hughes and Fisher noticed is if interaction between particles depends on the distance between them, that is often the case in reality, right? There are two types of domain walls. The one that brings particles closer to each other would cost you more energy than the one that brings particles further away. I can continue this logic and say that the sequence of domains A, B, C would cost me a different energy in sequence A, C, B. This, according to Hughes and Fisher, create chiral perturbations that might affect the nature of the phase transition. So they arrive with the following sketch of the phase diagram. There is one single line where there is no chiral perturbation, and along this line, the transition would be in three-state Potts universality class precisely as what we would expect from naive symmetry arguments. But away from this line, they say that there is a possibility of a new direct chiral transition in a different universality class, until eventually chiral perturbation becomes so strong that the melting becomes a two-step process with intermediate critical phase, incommensurate phase, separated by Pokrovsky-Talipov transition with the dynamical critical exponent 2, the one that you mentioned yesterday, and a Kosterlitz-Zales transition. And almost immediately after, this proposal has been confronted by field theory, by Hallen, Bach, and Bohr, who say, wait, in the absence of chiral perturbation, yes, the transition should be in three-state Potts universality class. When chiral perturbations are strong, we agree there should be a critical floating phase in commensurate light and liquid. But there is no room, according to our field theory, for a direct chiral transition. So this intermediate floating phase should extend all the way through till the Potts point. The year after, there came a counter-argument by Hughes and Fisher saying that this picture is valid only in zero fugacity, or now speaking in terms of quantum chains, in the absence of quantum fluctuations. As soon as we allow some quantum fluctuations, we open an opportunity for chiral transition to appear. This is an amazing example. The theory debate was not solved at the time, precisely because numerics at that time was not powerful enough to resolve this critical regime, despite the fact there was already experimental observation of this new chiral transition. You see here an example where in experiment they measure delta Q times Xi. I'm going to come back to this quantity later, in silicium monolayer and germanium monolayer. And you see the behavior is completely different. In one case, it goes to 0. That would correspond to a chiral, to a conformal three-state Potts point. And in another case, it goes to a finite value that would signal the presence of chiral transition. Well, numerics at that time could not help, and theoretically the problem remained open. But now, in this new context, in the context of quantum 1D chain, and thanks to a very talented guy who is located 150 miles south from here, I'm speaking about Steve White, we also have an amazing, powerful tool to address this problem numerically in quantum 1D. So this is done with density matrix renormalization group algorithm, and I'm not going to go into too much details, but I'll try to give you a flavor of what the algorithm is about. So the main problem of quantum many-body physics is that the Hilbert space grows exponentially fast. And with exact generalization, we can treat a few dozen sites, not more. But, as has been stated already quite a few times in this workshop, there is an area law that tells us that low energy states of local Hamiltonians are less entanglement than a random state of the Hilbert space. So the key idea of DMRG, at least how we understand it now, is to try to diagonalize the Hamiltonian directly in this corner of the Hilbert space characterized by low entanglement without ever writing down the full matrix. But it turns out that naive DMRG, the most simplest version, still gives not enough accuracy to resolve this problem. And what we actually need to do is to look at the simplified model. So we approximate the 1/6 van der Waals interaction by a blockade and a next to blockade interaction. And this leads to a reduction of the Hilbert space. So the Hilbert space still grows exponentially fast, but much slower than the unconstrained one. But more importantly, it also leads to a very efficient implementation of the blockade that we can treat as sort of local symmetry and bring the tensor networks to the block diagonal form, and this drastically reduces the complexity. I'm not going to give you detail, but I'm happy to discuss it with you offline. But what does it mean? It means that at the criticality, or close to criticality, we can reach system sizes about 9,000 sites. This is much larger than accessible with other techniques. And this finally gives us enough accuracy to resolve different critical regimes. Of course, such a blockade model doesn't give me access to the whole phase diagram of Rydberg blockades, but it gives me an opportunity to look at the slices through the blockade, through the phase diagram. So with nearest neighbor blockade, I can take a look at the top of the period 2 phase and tip of the period 3. I increase the range of a blockade to next nearest neighbor, and then I can explore top of the period 3, tip of the period 4, etc. So it's not like a universal model, but still it gives a good idea and a good opportunity to explore quantum phase transitions. Now, from the theory of Hughes and Fisher, we know that in principle there could be 3 different scenarios for the transition to the period 3 phase. 3-state pods, chiral, or floating phase. And they also give a recipe how to distinguish them. So they propose to look at the quantity delta Q times psi. Remember, that's precisely the one that has been measured in experiments in '94. And they tell that when transition is conformal, the product goes to 0. When it is chiral, the product goes to some finite value. And when the system goes through a latent liquid phase, what happens, it first goes through a Kosterlitz-Zales transition that is not affected by commensurability. What happened there, delta Q doesn't change across the transition, but the correlation length, as we know, diverges stretch exponentially. So the product of the two also diverges and diverges fast. So we extract both correlation length and the wave vector Q by looking at the density-density correlation. And here you see why we actually need so large system size. The main slope of the correlation function gives us the correlation length. But you can see there is also these regular oscillations that are precisely signaling incommensurability. And now if I remove this main slope and fit the rest with just a pure cosine function, I get my delta Q, the distance of the incommensurate wave vector to its commensurate value. And you can see how actually well our de-emerging results shown in blue agree with the fit. Again, this is just a pure cosine function, nothing special here, and the agreement is really spectacular. So we measure this quantity delta Q times psi across different cuts through the transition, and we come up indeed with 3 different regimes. There is a 3-state pods where delta Q times psi vanishes at the transition. There is a floating phase where the product clearly diverges upon approaching the Kosterlitz-Zales line. And there is another regime where the product delta Q times psi goes to a finite value, as Hughes and Fisher predicted for the chiral transition.
Are you tuning delta Q when you go between these different lines? How do you go between these?
So we are tuning the chemical potential or interaction, but this affects delta Q.
Delta Q, okay.
Yeah. More questions? So we could finally resolve it. Very nice. And if you look at the phase diagram, the transition out of period 3 phase is actually pretty complicated, right? There is one single point in the 3-state pods universality class. In fact, the credit for this point goes to Severe and collaborators because it is located on the integrable line. So for us, it was a very important benchmark of the algorithm. But then this particular conformal point is surrounded by non-conformal chiral transitions until eventually we open a floating phase. And now you see why it was actually so difficult to detect it, because the width of the floating phase is smaller than the red line that you see on the phase diagram. Of course, realizing such a zoo of quantum phase transition in period 3 motivates us to look further and to look what would be the nature of quantum phase transition out of period 4 phase. Yeah.
So about this transition line, floating phase, is that a transition period? Is that a critical point? Or is it...
Floating phase is indeed a critical phase with 2 transitions. So imagine this line is actually a phase, very narrow, but a phase. And there is a Kosterlitz-Zauerless transition on that side, a Pokrovsky-Talopov transition there. And there is a floating phase is a Lagrange liquid phase, so it's C=1 phase, but with incommensurate quasi-Lagrange order. Yeah?
And the three-state path transition is separated to chiral transition?
Yeah. Yeah.
Two chiral are the same.
Yeah, they're very similar, yeah. So, let's look what's going on at the period 4 phase. And in fact, our starting point here was actually much weaker, because for the period 3, yes, we had no solution. You know, we had a debate with arguments pro and cons, but at least there were, like, you know, smart people giving their idea about this. For period 4, we had a very little information before we start doing numerics. The only thing that we knew for sure is that transition, the chiral perturbation, might not always be relevant. It means that even if there are some incommensurability, it might not change the nature of the conformal point. And if it changed, still there is a question how. So we start to explore, and this is basic phase diagram. Again, I'll look at the blockade model now with next nearest neighbor blockade, and no surprise, I see a top of the period 3 phase and tip of the period 4. What I'm going to do now, I'm going to focus on this phase transition to the period 4 phase. And the first question is, if there is a conformal point, how to locate it? Before, we had an integrable line. Now we don't. So what I proposed, and it partially answered the previous question, is to look at the wave vector Q all over the disordered phase. And obviously it goes from 2 pi over 3 close to period 3 phase to 0 somewhere at infinity. But eventually it passed through the line with Q equal 2 pi over 4 that would be commensurate with the period 4 phase. So along this line, there is no chiral perturbations for this transition. This is a hypothesis. Let's check. So sitting at this crossing point, we measure the scaling dimension of the operator that would be an order parameter for the period 4 phase, and the central charge conformal anomaly. And both of them agree with what we would expect for conformal point here for the Ashken-Teller universality class. Good? So what we have is an Ashken-Teller point. Now we start to look around. And again, we can use the same criteria proposed by Hughes and Fisher to look at delta Q times psi, but now delta Q is really measured with respect to 2 pi over 4, right? It's different thing. And what we see is again 3 different regimes. When we approach the Ashken-Teller point, despite the large error bar that now comes from the fact that we don't know the location of the conformal point exactly, we see that it decays to 0. Then we see a regime very clearly of the floating phase with divergent delta Q times psi. And then there is a region where we see the delta Q times psi goes to finite value, indicating that again here we do have another chiral transition. So if I again try to put this all information on the phase diagram, we see a very rich quantum critical behavior with one single point in the Ashken-Teller universality class, again surrounded by yet another chiral transition that is followed by the floating phase. Questions now? So at this stage, you might wonder, okay, I did a simulation for a blockade model, it works well, but is it actually relevant to real experiments? What would be if I still come back to this van der Waals potential with 1 over R6 still, will I still be able to see it? So we examine the phase diagram, now with 1 over R6 potential, and we use the same trick to locate possible crossing where chiral perturbation vanishes and possible location of the conformal points in POTS and Ashken-Teller universality classes. And we'll look at the delta Q times psi for the period 3 transition on top and period 4 transition on the bottom. And you see that in one case, there is a conformal point with delta Q times psi going to 0. Then we find several cuts where we see chiral transition with clearly delta Q times psi going to a finite value. And we see a signature of the floating phase that was actually divergent so far, so we plotted inverse of it. But what you see is great, right? We find universality class, and we find that it's possible to realize them in an experimentally realizable model. So we should be happy, but in fact, if we take a closer look, what's going on in the following? At this point, we realize conformal transition. Right next to it, we realize chiral transition, but if you look already at this point, we see a floating phase. So chiral transition is present, but it's super, super short. And if we assume that there is still a noise and some uncertainty in experimental realization, it will be very unlikely that we will be able to see the signature of chiral transition clearly in this experiment. And in order to understand how to overcome this difficulty, we first need to understand why it actually happens. And the reason for this comes with little investigation of the chiral Ashkin-Teller model. So you see what happens. Even in the absence of chiral perturbations, the transition to the period 4 phase is way more complicated than transition to the period 3 case, because it belongs to the Ashkin-Teller universality classes, which is a big universality class, or if you wish, which is the whole family of universality classes that interpolates from the 4-state Potts point and to the coupled Ising chain. All the way between these 2 points, there is a conformal transition in the Ashkin-Teller universality class. But depending on where we are on this line, chiral perturbation might be irrelevant, or relevant and lead to a chiral transition, or relevant and directly open a floating phase. And what happens in Rydberg atoms is that the critical exponent of the correlation length is 0.78 that corresponds to this Ashkin-Teller parameter 0.57 that on this phase diagram sits right here, super close to this green Lifshitz point where chiral transition actually disappears. So we just have not enough room for chiral transition to develop. That's why it is so short. But come on, we identify new universality classes, right? We want to observe it. Is there actually a way to push a bit this Ashkin-Teller point such that we see a bit larger chiral transition so we could actually hope to realize it in experiment? And with this we come to tunable, the idea to tune quantum criticality to be able to zoom on the interesting part of the transition. Yeah.
During the 3 also the chiral transition was pretty narrow, right?
It's not that narrow.
Okay, well then it's already there, right?
No, yes, indeed, but you know, even in classical atoms, it was already observed. So, yeah. So
we still don't know the exponent z.
let's talk later. I think we know
From
from numerics, and it agreed pretty well with looking data for Z3, for period 3 case. Yeah, from numerics. But okay, coming back to the idea how to play with Ashkin-Teller point. Obviously, this phase diagram is 3-dimensional, and what we had before with Rydberg atoms is 2-dimensional, right? We have interatomic distance, we have laser detuning. So we need to increase the dimensionality. And one of the ways to do it is to look at the multi-component Rydberg areas. This is a pretty old idea that has been probed already quite a few times, but as you will see, it's actually a pretty powerful idea in the context of quantum phase transitions. So the setup is very simple. Again, we take ultra-cold atoms, we trap it with optical tweezers, we shine a laser, we excite it to a Rydberg state, but then we, instead of just one laser, we take 2. And when we shine one of them, it excites to one Rydberg level. When we shine another one, it excites it to a different Rydberg level. Now, it is possible to choose a level in a different way. And one way is such that the interaction between this blue component would be much weaker than interaction between a red component. We also can choose the level such that there's almost no interaction between these 2 components and no, kinetic term that would bring a system from one component to another without ever going to the ground state. So we essentially go into a model where we have 4 parameters, only 3 of them are independent, but 3 is precisely what we need to probe 3-dimensional phase diagram of the chiral Ashkin-Teller model. So let's see. I fix first the ratio of the Rydberg frequency to just, some random number, omega 1 over omega 2 to be 1. And then I vary the detuning of the two components. My red component has next nearest neighbor blockade, and when I favor the occupation of this component, I have obviously end up in the period 3 phase, which is maximally packed for this type of the blockade. If I do the same with weak component, I end up in the period 2 phase, where every other atom is occupied in this lower Rydberg level. But now, if I tune both components to be as occupied as possible, what happens is that every other site that was empty here, that was in the ground state, start to be excited in a strong component. So I end up in the period 4 phase. So looking here, you can see that we can go from a disordered phase to period 4 in two different ways, right? We can go through double Ising transition, one by one, or eventually they actually come together, merge at the multi-critical point in the Ashkin-Taylor universality class, and then we can cross it again through a chiral transition or through the floating phase. Now, here I fix the ratio of the two components. What if I vary it? So, for the ratio 1, I have a critical exponent 0.76. Remember, for a single component, it was 0.78. That's pretty close to what we had before. If I tune the ratio to be 2, I push my nu to be 0.68. Pretty far already. Quite good. And if I do it oppositely, my nu increases a lot. Actually, it increases to the point where there is no chiral transition anymore. So you see, by tuning this delta 1 over delta 2, the ratio of the Rydberg frequency, I managed to manipulate the nature of my Ashkin-Taylor point, and I can tune it along this line. Now, let's see if actually what I wanted to see, if it affects the nature of the extent of the chiral transition. I guess you can already see it. So if I very naively estimate the width of the phase transition, you see that by tuning the ratio of delta of Rydberg frequencies, I actually gain basically a factor of 2. And here, it disappears. I was not able to see it. I cannot claim it doesn't appear at all, but at least it's width smaller than 0.1. So with this, I come to my conclusion. You see, with multi-component Rydberg atoms, we can go from qubit to qubit, right? We can enlarge the Hilbert space such that we basically open the possibility to manipulate quantum phase transition, to probe quantum phase diagrams that are in a multi-dimensional parameter space, but yet we do not mess up with symmetries. Of course, it's not the first proposal on how to create qubits out of Rydberg atoms, right? And the simplest one is just to create a ladder. But in ladder, you have two symmetries. You have a symmetry in this direction and symmetry in that direction. In multi-species Rydberg arrays, when you mix up cesium and rubidium atoms, for instance, you, by construction, by arranging the pattern of your cesium and rubidium, you break translation symmetry. Here, everything that happens spontaneously. And that's why I think multi-component Rydberg arrays are really an ideal playground in the context of specifically quantum phase transitions. Now we can manipulate quantum phase transition, but who knows, maybe in a few years we could even construct a new one directly in experiments. So with this, I would like to thank you for your attention and looking forward to your questions.
Excuse me. I wonder this Ashkin-Taylor critical point is a conformal. So it does a central charge 1.
Yeah.
Okay. And but its radius is fixed to some value.
Sorry.
Whether it have SU2 emerging symmetry or central charge 1 have a marginal direction, so there's a radius. Whether there's some particular radius here.
If I'm not mistaken, this one is not fixed. It also varies.
Oh, I see. It's varying.
Yeah.
Okay.
Yeah. So the only universal thing that is fixed, a part of the central charge, is the scaling dimension. Okay. At least first, it has been established numerically. Okay. So I guess now when
So you also have a chiral line. That's also conformal fixed point?
No, chiral transition is not conformal. It has dynamical.
But it's continuous transition.
It is continuous transition. It's direct transition, and it has dynamical critical exponent larger than 1. But
dynamic exponent is not equal to 1. I see.
No, it's not equal to 1, but still it's like 1.1, 1.2 from numerical data, so it's not too bad. But
I see. Not 2, but the 1 point.
Not 2.
Oh.
No, it's not.
And you also have the floating one.
Yeah.
Floating one is also dynamic exponent not equal to 1.
No, floating phase, if we do not look at the Pokrovsky-Talapov transition, but the whole phase and the Kosterlitz transition has C equal 1. So this is a latent liquid phase. The Pokrovsky-Talapov transition is C equal 2. Oh, sorry, Z equal 2. It's not conformal.
Okay, now, thank you.
Chiral transition is one of the very rare strongly coupled fixed points, which is not conformal.
Maybe already the question is also whether the other phase, but this is a little bit, but this is a little bit strange, because all the phases involved are commensurate, right? Do you have incommensurate phase?
Oh, no, they're not commensurate.
The floating one is incommensurate then.
Floating one is incommensurate, but disorder phase almost.
Okay.
Let me see, maybe this. Oh, here. So everything in blue is a disorder phase, or in white, sorry. And it is incommensurate. So what you see in
white
line,
one is incommensurate.
Yes. So you see this is a wave vector Q in the function of 2 pi.
Oh, I see.
The commensurate part is this one is in black. So around 1/2 lobe, it is commensurate.
Okay.
But away
No,
from
I
it,
understand.
no.
I see. So here you have U1, you have U1 symmetry. So when you change density, it's
emergent
incommensurate.
in the floating phase.
Yeah, sorry. So can you explain the logic again about determining the chiral and so on from this numerical data plot of Q minus Q star times something? Yeah, you are just showing this. Yeah.
This one.
No. Something. Yeah.
Okay. So the point is, instead of the normal order parameter in the chiral transition, precisely because we have incommensurability, we use a different order parameter, which is delta Q. Mm-hmm. And if we would say that with normal order parameter, we would measure critical exponent beta, delta Q scales with a different critical exponent, we call it beta bar. Mm-hmm. And now we don't really know the exponent beta bar or nu for the chiral transition. But we identify this transition as such that where beta bar is equal to nu. Mm-hmm. And as a result, the product of the two, they vanish with the same exponent, right? That's why the product is to go to.
I see. Okay. You explained in this slide. Okay. Somehow I was not following. Thank you. Another question is that, period 3 is related to ports at least at the special point, and the period 4 to Ashkin-Terra, which is kind of natural. And what about period 5?
This is a good one. So starting from period 5 and above, there is no direct transition anymore. Everything is covered with a floating phase.
I see.
It has been conjectured theoretically a long time ago in the 80s. It has been verified numerically. Now it's pretty well established.
Thank you.
So in general, what you have is from incommensurate to commensurate transition, like a period 4 is commensurate, but the other side is incommensurate. But however, we'll go along this line, at some particular point, you may have a commensurate to commensurate transition.
Yes.
Because the density happen to be commensurate in this disordered phase.
Yes, exactly.
And so at those particular point,
it's conformal.
It's conformal.
Yeah.
I see.
Yeah, exactly. And
so that is a P point. I see.
Yeah.
So what kind of critical point you see in those particular points? So like in Z3 case, do you see some pulse critical point?
Yes.
Oh, I see.
And in period 4, it's Ashkin-Taylor.
Okay.
And there is something, okay, this is now a subtlety, but I think it's an interesting one. Sorry? Few slides to go. Here we go. So you see there is a small narrow window of the orangish line. So it's precisely the window where chiral perturbations are not right away relevant. In this case, you might not see just one single point in the Ashkenazi universality, but intervals of the Ashkenazi, and then chiral transition, and then the forcing phase.
But for the period 3 case, equal to 3 case, you see pulse critical, but you don't see this multi-critical pulse. So there's two related. There's multi-critical. The pulse one is a 6-5 minute model. Multi-critical one is 7-6 minute model.
We don't see multi-critical pods.
Oh, I see. You just see 6-5 minute model.
Yeah.
Okay.
Yeah, it's just normal pods, and then right away that's chiral transition, and then at the point where we open the floating phase, this multi-critical point is Lifshitz point with z equals 3. So it's a different one.
Any further questions?
Okay, maybe I can.
Not a question, but allow me to advertise some of our work. So this is work by Seth Whitsitt, my former student. So we did a 2 minus epsilon expansion of this chiral transition, starting from z equals 2 in d equals 2. And it's quite complicated, but it gives some results that Seth worked out.
Thank you.
Maybe I will ask a question. Is there, like, if you do the MRG on cylinders instead of 1D systems, can you extend some of these phases to 2D?
That's an excellent question, and I'm not going to answer it today.
Okay. All right, so let's thank Natalia again and thank all the speakers for interesting talks.
Maybe I'll take the opportunity to thank the organizers for a wonderful conference. I mean, I guess you're all here, Yushi and Avishkar, and who else? Alex. So thank you very much. Great conference. Really enjoyed it.